A cooling tower is a large heat rejection device that removes waste heat from industrial processes or HVAC systems by bringing hot water into direct contact with air, using a small amount of water evaporation to cool the rest, releasing heat and vapor into the atmosphere. Cooling towers are crucial for removing waste heat from industrial processes and large HVAC systems, preventing equipment overheating, boosting energy efficiency, cutting operational costs, and ensuring machinery longevity by using water evaporation to cool hot water, making them essential for power plants, chemical facilities, data centers, and manufacturing. Key functions and importance. Heat rejection. They efficiently transfer excess heat from water to the atmosphere, acting as large heat exchangers. Process. Cooling. Essential for cooling water used in condensers, distillation, and other heat-generating processes in industries like power generation, oil refining, and food processing. Energy efficiency. By maintaining optimal operating temperatures, they reduce the load on cooling systems, lowering overall energy consumption. Equipment protection. Consistent cooling prevents thermal stress, extending the lifespan of machinery and reducing maintenance costs. Water conservation. They recycle water within a closed loop, minimizing the need for freshwater intake and reducing waste. Cost savings. Improved efficiency and reduced water energy use lead to significant operational cost reductions. How they work. Simplified 1. Hot water from equipment is pumped into the tower. 2. The water is sprayed over fill material, increasing its surface area. 3. Fans draw air through the tower, causing a small amount of water to evaporate. 4. This evaporation process cools the remaining water. 5. The cooled water is then recirculated back to the equipment. Key applications. HVAC. Cooling large commercial buildings, hospitals, and malls. Industrial. Power plants, including nuclear, chemical processing, and manufacturing. Types. Mechanical draft. Uses fans to move air, most common in HVAC. Natural draft. Relies on the buoyancy of hot, humid air to create airflow. Large, hyperbolic structures at power plants. Dry cooling towers. Use radiators instead of evaporation, losing no water but generally less efficient. The performance of cooling towers is evaluated to assess present levels of approach and range against their design values, identify areas of energy wastage, and suggest improvements. Measured parameters are wet bulb temperature of air. It is the lowest temperature air can reach by evaporating water into it, measured with a wet cloth-covered thermometer. Dry bulb temperature. It is the standard air temperature measured by a thermometer freely exposed to the air but shielded from moisture and radiation, representing the actual heat content. Cooling tower inlet water temperature. Cooling tower outlet water temperature. Exhaust air temperature. Electrical readings of pump and fan motors. Water flow rate. Airflow rate. Range. It is difference between cooling water inlet and outlet temperature is called range. Range, degrees Celsius, equals cooling water inlet temperature minus cooling water outlet temperature. Range equals 42 minus 32 equals 10 is the range. High range indicates the good performance of cooling tower. A high cooling tower range means that the cooling tower has been able to reduce the water temperature effectively and is thus performing well. Approach. It is difference between cooling tower outlet, cold water temperature minus wet bulb temperature, 32 minus 28 equals 4 degrees Celsius is the approach. Low approach equals good performance. The lower the approach, the better the cooling tower performance. Although both range and approach should be monitored, the approach is a better indicator of cooling tower performance. Effectiveness of cooling tower. Effectiveness in percent equals range divided by range plus approach equals 10 divided by 10 plus 4 times 100 equals 10 divided by 14 times 100 equals 71.42%. Hence, effectiveness of cooling tower is 71.42%. The higher this ratio, the higher the cooling tower effectiveness. High effectiveness equals good performance. Cooling capacity. It is heat rejected in kg, calories per hour, or tons of refrigeration. TR equals mass flow rate of water times specific heat times temperature difference. 4,000 times 1,000 times 1 times 10 equals 40 million kilocalories per hour equals 4,000,000 divided by 3,024 equals 13,227.51 TR. High cooling capacity is good performance. Evaporation loss. It is water loss by evaporation. Formula equals 0.00085 times 1.8 times flow rate times temperature difference. Example, 0.00085 times 1.8 times 4,000 times 10 equals 61.2 cubic meters per hour is the evaporation losses of cooling tower. Cycles of concentration. COC. It is how much time water is used inside the tower before being bled off. Ratio of dissolved solids in circulating water to the dissolved solids in makeup water equals 1,130 divided by 275 equals 4.1. Most of the tower runs 2 to 3 COC. Blow down or bleed off losses equals blow down depends on cycles of concentration and the evaporation losses. Formula of blow down equals evaporation loss divided by COC -1 equals 61.2 divided by 4.1 minus 1 equals 19.7. 4 would be blow down. Liquid gas ratio. L divided by G equals the L divided by G ratio of a cooling tower is the ratio between the water and the air mass flow rates. Cooling towers have certain design values, but seasonal variations require adjustment and tuning of water and airflow rates to get the best cooling tower effectiveness. Important properties of water. Total dissolved solids, TDS. Conductivity, hardness, alkalinity, pH, silica, other impurities, iron, phosphate, chlorides, sulfate, etc.